Okay, 4 o'clock. Let's start. So my name is Pavel Exner, and it is my pleasure to introduce the speaker at this public lecture, Professor Stanislav Smirnov, whom I would ask to unmute and show himself. He studied in St. Petersburg and at Caltech, and his field is complex analysis, dynamical system, and probability theory. And in these fields, he made a significant impact, as one can see from various prizes and awards he got. Among them, the towering one is the Fields Medal of 2010, which he got from the citation for the proofs of conformal invariance of percolation and the planar easing model in statistical physics. But it is not the only award. You get many more. I mentioned 2 more. It was the Clay Research Award, and since we are at the European Congress, the EMS Prize in 2004. And for this year laureates, I will add, it is an experimental fact that with probability 1/6, the EMS Prize is a precursor to Fields Medal. So pay attention. But back to the speaker. He is a professor at the University of Geneva. And he's at the same time the director of the Chebyshev Laboratory in St. Petersburg. And what is also important, he's one of the main movers of the ICM next year, which was advertised before this lecture. But I will not steal more of his time. So Stas, the floor is yours.
Hey, thank you very much, Pavel, for the nice introduction. So I believe you can see my screen now, everyone.
Yes, we do.
Yes. Yeah. Okay. So it's a well, great honor and a great pleasure to give a popular talk at the ACM. Of course, well, the pleasure is a little bit hindered by the fact that it's I cannot be for epidemiological reasons in person, and we really hope that at least next year ICM will bounce back to the normal life, which all missed so far. And I would want, before starting the talk, thank the organizers from Slovenia, because it's very difficult to navigate through these circumstances. Now, with popular talks, it's always a big problem because you don't know the audience. It happened to me, like learning half an hour before the talk, I was supposed to give to 300 kids that their age is uniform between 7 and 17. And I had to urgently redo the slides. Now here I see that probably, I was told that mostly it will be for the general public, but I see here many smarter mathematicians in the audience than myself. So I will try to cater to both. And I will start with some sort of question which often lay people ask mathematicians whether mathematics is art or science, because they often hear that we do it mostly for aesthetical reasons. Well, there is actually one art piece by Raphael where you see many philosophers and famous mathematicians of antiquity. For example, in the bottom right corner, Euclides showing to a group of students his theorems. So the first question, so what is mathematics? Maybe we should start with the question when it started. It started about 4,000, maybe 5,000 years ago. And what I find really exciting and interesting is that the motivation hasn't changed much, at least from what we can deduce from what we see in the museums, from what our colleagues did 4,000 years ago, that there are problems which arise from practical applications, from engineering back then, or artificial intelligence nowadays, applications from other sciences, where once in a while our friends physicists or more recently biologists or economists come with questions. But also there is a beauty and cultural value, like Pythagoras' theorem was appreciated by the Greeks for its beauty, not only for its use, but more modernly there are like many things which can be appreciated by general public. And what is even more exciting that these three motivations mix. I will start with a few historical examples. So what happened is that like 4,000 years plus, people began to notice interesting patterns in nature and in astronomy, physics, geometry, arithmetics. And originally they were attributed to magical divine nature, but then first scientists started trying to explain them. And I want to show 3 artifacts which you can see in museums. So if you have an ICM next year in person, you can go to Pushkin Museum of Art in Moscow to see this one, or we'll hope to exhibit a copy of it at the ICM. So it's one of the oldest mathematical manuscripts, probably the oldest. It's called Glenishev Papyrus by the name of person who bought it at a market in Cairo, and it dates to about 2000 BC, and it's based on earlier scrolls. And it is a collection of problems which is not so different from today's GRE or A levels. So for example, well, most of it is some arithmetics or algebra, so not knowing the alphabet, you can hardly decipher because people didn't use formulas back then, they rather wrote everything with words. But this is the part which is exhibited now. It's rather long. It's about that wide, 10 centimeters wide, and its length is over 7 meters. So the problem which is exhibited is the find the volume of a cut parameter of the frustum. So given that it's bounded by squares with size 2 on top and 4 on the bottom, and the height is 6, and then there is a formula without a proof. And well, that is sort of clear that most likely it was a practical problem, Egyptians being famous pyramid builders. So it's not surprising, and all the other problems you have there, it's how much barley you need to produce, well, 5 barrels of beer, or how long should be the mast of a ship if something and something. And maybe the most interesting is that the problems are very much like what you see today on A level, so we haven't advanced that much in 4,000 years. But there are more interesting things which come from Babylon. Maybe Egyptians were more practically oriented. And this is a clay tablet, which is probably something used by a student during his calculation, so it's not very accurate. You can see it in Yale Babylonian collection. It's actually in the room next to the one of the Gutenberg Bibles, which belonged to Cardinal Mazarini. So it's about that big, and it had some, well, it has a picture of square with 2 diagonals, and it has some calculations. So the calculations here are cuneiform. And well, one must understand that the system was hexadecimal, so the digits are from 0 to 59. But strangely enough, well, okay, it's hard to come up with 59 different symbols. So Egyptians, they use decimal system to write their hexadecimal digits. So here you can see the number 1. Well, it's just 1 line. Then 2 and 4. So 20 is you draw it in a different direction, and 4 are 4 vertical. So it's 1, 24, 51, 10. If you know that it's hexadecimal system, you can just add, and you get the number 3005 and 470. And the question is, what does it have to do with the square, and what is this number? Now the trick is that Babylonians, they did not have the notion of a decimal point or a hexadecimal point. So they just inferred from the context where it should be placed. And here the context is that it should be placed before the number. So actually it is a fraction, and it's 1 plus 24 over 60 plus 51 over 60 squared, and so on. And if we calculate, it's the same number as on the previous slide by divided by 216,000, and it's 1.41421296. So, well, everyone would guess this number because we have seen it in school lessons. So it's approximate value of a square root of 2, and at that it's a very, very good approximation. So what I must note that back then there was no practical reason to calculate with such precision. Even nowadays, if you're building some high precision machine and you need, for example, some part which should be exactly square root of 2 the length of the other part, then probably 4 decimal points would be enough. So it's really an interesting question why a student did this. Especially, it's not a sort of definite paper. It's just kind of notes used for calculating, and probably curiosity was motivation, or maybe it was an exam problem and one was training to do some other more practical calculations. And this is even not the most exciting or interesting of the Babylonian tablets. So this is, by the way, yeah, there is a second row of numbers, 42, 25, 36, and this actually is the same thing, but when you have a side of triangle 1/2, or about the same if you multiply by 60, 30. So so first someone calculates square root of 2, and then someone calculated the length of the diagonal when you have the side 1/2. So this is not the most exciting of tablets. There are many more, and it's so happened. So everyone has heard of Library of Alexandria, but somehow the library on which it was modeled was less famous because it was modeled of the library of King Ashurbanipal, or another name he's more often known under the name Sardanapal. So he lived about 600 something years BC, and he owned a huge library, the biggest one of 30,000 clay tablets. Now, what happened back then, that at one point, well, he was appointed king by his father, being the second brother, because his father thought that he is the smartest. And once when he was expecting around the country, his older brother threw a revolt, and he didn't want to burn down the capital, so he sieged it for 2 years. Eventually, his brother burned it down, and the whole palace with the library collapsed. But since it was not a papyrus library like in Alexandria, but rather a clay tablet, it survived. It was discovered 170 years ago. Now most of it in British Museum. And they had 3 years ago an exhibition, a really fabulous exhibition. So I have a few pictures I made back then. And there is everything, like from magic to medicine, from astronomy to mathematics. And this king was really educated. So there are some portraits of his, and while his contemporaries usually, or well, later kings or presidents usually boasted of military prowess, he writes, well, he writes also about military things, but he emphasizes that he is very learned person, that he speaks Akkadian language, which very few people understand, etc., etc. And he has read all the esoteric books. And then there are even mathematical parts that I can solve mathematical problems which defy an easy solution, which very few smart men can solve. So one of the tablets from this period, so this is in this exhibition, it replicates an older one from Babylon, which is about 1,000 years old. And this one you can see at Columbia University in New York. And you immediately see that it's a tablet which has 5 columns of hexadecimal numbers. So 2 of them are just numbered 1, 2, 3, and so on. So the one on the right, for example, you see that it's 1, 2, 3, and so on. And if you decipher, it's fairly easy to decipher. Then, for example, here you have 159, 249. So if you rewrite them in our decimal system, it's 119 and 169. And the question is, why are so many numbers? You see really big ones here. And it turns out that those are the list of Pythagoras triples, so the triples of integers, so that a square plus b square is equal to c square. Only one of the columns is missing because you can easily solve for the remaining one. For example, in this case, the remaining one is 120. And the smallest known triple, you learn it in school, is 3, 4, and 5. Quite likely, since Babylonians produced so many triples, they knew the Euclid formula, which essentially gives all the triples, well, up to multiplication. So a is u square minus v square, and c is u square plus v square, and you can plug in u and v. And one can see the need to calculate the first one. For example, this 3, 4, 5, it was used by Egyptians to do some trigonometry when they did some agricultural planning. It's probably the easiest way to do an angle of 90 degrees. You just take 3 pieces of rope of the length 3, 4, and 5, and then the vertices of the resulting triangle will give you a 90-degree angle. But why do you need more triangles? And what is this this other row of large numbers? So it's a hot topic of discussions between historians. And one must say that the first this Babylonian mathematics sort of stayed hidden before late 19th century. And then one of the students of David Hilbert, Otto Negenbaum, he wrote several books. And now there are more tablets which are digitized and deciphered. So there is a hot topic why it was all done. So I would probably think that the most reasonable conjecture that it was some sort of trigonometry application for astronomy and architecture, because they didn't really have a notion of cosine or sine, and they tried to operate with rational numbers. So this allowed to some expressions of cosines and sines for a fairly dense set of angles, which would be very, very important for astronomical observations. And we know that Lewis were very good at those, and they really did tremendous work in astronomy. And the other conjecture is that scientific curiosity is the motivation. Why do we need really so many of them? By the way, the interesting thing that this tablet, it has actually two typos in the middle. So it's a question why, well, how they did it and how they arrived at the typos. So what is interesting is that Babylonians, they wrote these huge forms. They probably know Euclid's formula, and they knew, probably without proof, Pythagoras' theorem. Certainly they and Egyptians used it. And this question of finding integer numbers, it's originally was motivated by geometry, because they saw the triangles, but then it's a purely arithmetical question. And interestingly enough, we don't know about Babylonians or Egyptians, but Greeks asked whether there are solutions to these equations with higher powers. Say 5, 4 also has some geometric meaning. And it took till, well, almost 2000 years, till Pierre Fermat, to prove that there are no integers with integer solutions with power 4. And as everyone knows, only 26 years ago, Andrew Wiles proved finally that there are no positive integer solutions to any power n. And the interesting thing that many similar questions are still open. So for example, if you ask the same question with arbitrary 3 different powers, then it's wide open whether there are solutions which are not mutually prime. And that's not even the most important question. It's the easiest one to formulate in this area. So sometimes you have these connections really not only sort of across different areas, mathematics or applications, but way across of hundreds and thousands of years. Now, one thing which is interesting, which you observe already here, is some sort of beauty of mathematics, what mathematicians find beautiful. So it can be a short explanation of a difficult formula. For example, you write this whole tablet with Pythagoras triples, and then there is one formula which gives them all. A complex yet elegant theory, unexpected connection, and already here in Pythagoras theorem, you see a very unexpected connection between geometric object, the circle, and the formula x squared plus y squared equal to r squared, which gives the circle. And this connection between geometry and algebra has been sort of a main staple of mathematics for many, many years. And people often quote what Hermann Weyl said, that in these days, the angel of geometric intuition, the devil of algebraic abstraction are fighting for the soul of every mathematician. Well, it's a little bit of a misquote, because he said it about algebraic topology, and still many people would argue who is the angel and who is the devil. But it's interesting that this contraposition, it appeared more than 2000 years ago, and still it plays an important part in our lives. And Henri Poincaré said that mathematics is the art of giving the same name to different things. I would also add that it's also the art of giving the different names to the same thing. So it's really a part what makes our science interesting and beautiful for us. Now, the proofs of Pythagoras theorem, there are really myriads of those. So for example, the original proof of Euclid, it's a nice arrangement of triangles and squares. And there is a proof which is attributed to Leonardo da Vinci, where you make 2 copies of this triangle on top and bottom square, and then you rotate this quadrangle and you get another combination. And also a related Parseval theorem, which is a multidimensional version, and has a rather nice proof with the scalar product. So it's purely algebraic thing, seemingly with no geometry involved. So this is what we all think beautiful. But the problem is that often it's difficult to explain to non-scientific people, because mathematics is an acquired taste, and to appreciate it, one has to study. So of course, we all study mathematics for 10 years in school, but many people complain that the lessons are dull. So perhaps this is a fault of us mathematicians not improving the textbooks. And an analogy which I would make is music. Like we all appreciate music, or most of us, when it sounds. But if I show a piece of notes like this, this one by Beethoven, anyone with good musical training immediately will say that it's very beautiful, whereas those of us who hasn't gone to musical school, they will just say that it's not clear what that is. Whereas when we hear Moonlight Sonata, well, it's universally considered to be one of the masterpieces. Similar in mathematics, here on the left, it's a formula which is a good candidate to be the most beautiful formula. So Leonard Taylor's formula for E and pi, and again, without mathematical training, it's just a combination of letters. So how do we, well, there is this beauty, but can sometimes you show it to other people? Well, in analogy to music, well, one possible thing is that there are some problems which where you can draw pictures. So this is, for example, two objects which I've studied in my life, and the one on the left is this question from physics motivated by crystal growth. It's called diffusion limit aggregation, and you get beautiful coral-like shapes. And well, you can see that they are very interesting, and still can say very few things about them, though there are many conjectures. And on the right are Mandelbrot fractals and Julia sets. Again, the pictures are beautiful, and also you can put them in motion. So there are these holomorphic motions like below, which you can study if you know them, but you can see their beauty even without mathematical training. But those are other special examples. So when you deal with formulas rather than pictures, it's much harder to achieve. Now, the question is where mathematicians get their ideas from. And here it's interesting that several revolutions in mathematics, influx of new ideas came from physics or other areas. And the most famous example, it's the Newton's law of gravity. And it started with people observing for thousands of years. Even with honest, they made very good observations of suns and the planets. But then a leap happened when Tycho Brahe made much better calculations. So he had these long tables, and his assistant Johannes Kepler, he analyzed the data and noticed three empirical laws: that each planet moves along an ellipsis with the sun at its focus. The radius swipes the same area during the same time. So when it is closer to the sun, it moves faster. And the squares of the periods are proportional to cubes of the semi-axes of the ellipses. Actually, it's really unbelievable how one can notice such things without a computer, especially because the planet orbits are not the ellipses with high eccentricity like pictured there, but eccentricities are very small. So it's really a question of calculating like fourth or fifth digits. But when Kepler noticed this, it became clear that there is this really beautiful law. And the question was whether there is just some divine will which forces them move like that, or there is some other explanation. And that was the sort of beauty of Newton's idea that there is only one formula which will not only imply all these three laws, but also will describe the trajectory of a stone thrown. And it's interesting because, well, it's a beautiful idea, but to really put in motion, he had developed to a whole new area of mathematics, mathematical analysis. And that's not the only revolution. For example, one can argue that the revolution made by Fourier with Fourier series, it was sort of comparable value to mathematics, create all new areas, and in parallel it advanced our understanding on physical world. But also both these revolutions, they introduced many problems of interest to mathematicians and many beautiful objects. Now, why physics is related to mathematics? Mathematics is so esoteric and physics is rather practical. It's really a big mystery. And here there is an overquoted piece by Nobel Prize winner Evgen Wigner. And it's this essay. If you haven't read it, I really encourage it. It doesn't get old after 60 years. And he starts his essay with a sort of imagined conversation by two childhood friends, one of whom became statistician, and another one, a lay person far from mathematics. He asked him what he's working on, and the statistician pulls out his latest reprint and shows some formulas. And the guy says, oh, complicated formulas for what do you study? And he says, well, I study the population traits, for example, the average height of people, or for example, in this graph, you have the exam scores in in the United States in 2010. And you have this normal distribution, the Gaussian distribution, and he shows the formula, and he explains variation, he explains the mean. And then his friend asked, what is this symbol on the right? And she says, oh, this is pi. And what is that? Well, you studied in school. It's the ratio of the circumference of the circle to the diameter. And then the classmate says, well, you must be really pulling my leg. Surely the population has nothing to do with the circumference of the circle. And on one hand, it seemingly is true, but on the other hand, it's what makes mathematics beautiful. Then seemingly unrelated things, they often come together. So it's like in Euler's formula, we also had pi, though it was a formula about e the base of natural logarithm. So this is a historical thing, and I thought that it would be amusing for general public, or maybe even for some of my fellow mathematicians who haven't seen it before. But what I found the most exciting is that there is sort of continuity in what we do today. And okay, we cannot, I can't claim that I do something comparable to Fourier or Newton or the guy who came up with Pythagoras theorem. Probably it wasn't Pythagoras, but someone in Babylonia. But still, even if you do some interesting research today, it rings the same bells. And the question which members of general public ask, well, after they are dissatisfied with using pi for population density, does something happen in mathematics today? Because from school, you get an impression that everything was proved by Euclid or Pythagoras, well, or maybe Gauss or Euler, but still centuries ago. And the interesting thing is that after 5,000 years, there are still open problems, because whenever we prove something, new things come up, and sometimes more interesting. And also there are new practical problems and problems from other scientists which appear. So I will, well, I sort of hesitated whether to speak about some things which other people do, which would be maybe more appropriate, or be selfish and speak about some my own experience. And then I settled for the later, because then I sort of can add some personal reminiscences. And I will speak about two problems. And one is a purely mathematical question, and I will start with a sort of an easier question, which most mathematicians or physicists, they learn in the answer in the second year of undergraduate studies. And the question is, starts with a innocuous question: how many curves, that is broken line, you can draw in a grid? So here I did a honeycomb grid and a square grid, and you start drawing, so you get pictures like that. You go, for example, right, up, down, down, left, and then you double back and so on a hexagonal lattice. Again, you go in various directions. So here it's not only a mathematical question, but it came first to mathematical literature from physics, or rather even from biology. So Robert Brown, a Scottish botanist who did other things as well, he observed under microscope erratic movement of small particles inside vacuoles of pollen grains. So usually they write in the literature that he observed the movement of pollen grains, but grains of pollen that are too big to undergo Brownian motion. So the model, which was suggested by several mathematicians and first analyzed numerically by none other than Albert Einstein, was that invisible molecules, they bump into these minuscule particles and force them to move in random directions. So if you do it on the grid, the simplest model is that at each vertex you toss two coins, and depending on the result, like tail you go north, head you go west, tail go south, and tail you go east. So you get trajectory like that on the left. And if you plot the trajectories at the actual microscope, you see very, very similar things. So this is an example at a higher scale, and it goes a bit faster than the one on the right. Now, you can also do it in dimension 3. So this is, well, it's hard to observe under the microscope, but this is an example of numerical simulation. Or you can do in dimension 1, in which case you can, well, you can draw it on a line up and down. But the best thing is to plot the graph. And here there are several graphs plotted for 100 steps. And it immediately comes up as a good analog to many other phenomena you see in nature and in human society. For example, the price of stocks has this Brownian part because besides some general tendencies, like something might grow more expensive because there is a war in the Gulf and the oil is getting more expensive because of that. But also there are many people, many small entities, people, companies which buy and sell stocks independently for their own reasons, and that adds this sort of random walk. So what one can say about it? So first the question is I asked is how many curves or broken lines you can draw on a grid. And this is a very easy question because on the left you can at each step go in 4 different directions. So the number is just 4 to the power t, because each step you go in 4 different directions. So it's just the same question is how many words of length t you can write with an alphabet of 4 letters. Now on the right is 3 to the power t, so the base changes 4 and 3 because there are different lattices, but again it's exponential behavior. And another question you can ask is how far you go away after t steps. And if I go back 2 slides, you see that after 100 steps, you don't go 100 away. You on average go like 15 away, so or sometimes less. So on average about 10, so sometimes 5, sometimes 15. And this is a very nice and easy exercise. So you want to calculate the average value of the distance. But it turns out that it's the best to calculate the average value not of the absolute distance, but its square, which mathematicians denote by E, which is E for expectation in English, or well, first it was for espérance in French. And expectation of x squared at time t, you can just express as the sum of increments of steps. So there are t steps plus minus 1, and take the square. And you open up, when you open up a plus b squared, you have terms of the types a squared, but also terms of the types twice ab, and into which you plug in plus minus 1, and then a miracle happens, because whenever you have term twice as I as j, each of them is plus minus 1, and on average, if you have product of 2 independent plus minus 1s, you get 0, because they can either be both positive or both negative, in which case you get plus 1 as a product, or of different sign, and then you get minus 1, it cancels out. So we only get the diagonal. So instead of t squared terms here, instead of t squared terms, you get only t terms. And each of them is 1 because square of plus minus 1 is 1. So you get expectation to be equal of expectation of sum of t1s, the t. So x squared on average is equal to t. And absolute value of x is on average equal to square of t. It's a little bit strange because if you walk during time t, you expect to walk away time t times your speed. But here you walk back and forth, so it's logical that you don't walk that far. And it has a lot of physical consequences. For example, this is a heat equation, so it describes how the heat travels through the room. And that's the reason why if you don't have some convector or ventilator, then it takes a lot of time to heat a room with the radiator. So we really should, because the heat propagates with this square root law, unless you have some convection. So this is an easy and classical problem. Well, again, it took Albert Einstein to do it, but now 150 years later, it's easier. But let's ask another mathematical question. What if the trajectory is simple and self-aware? And I perfectly remember, I heard this question when I was in the first year of undergraduate studies from Anatoly Vershek. And back then I tried to do it for a couple of weeks, but it turned out to be too difficult. And retrospectively, I have not known that it's connected to so many things in physics and other areas of mathematics. And the question is how many trajectories you can draw if they're simple, that is self-aware. It's very easy to show, it can be even given as an exercise to high school students, that this number c of t grows as some mu to the power t. The question, what is the value of mu? And it's an easy, well, slightly more difficult exercise that mu depends on the grid. For example, for square grid, mu is between 2 and 3. And for hexagonal grid, it's between square root and 2 of 2 and 2. So they certainly are different. Well, non-strict inequalities are very easy to prove, strict are a little bit more. And then another question, it's a bit more complicated one, is what is the average distance? So we know that for random walk, average distance is square root of t, so t to the power 1/2. So here we expect that it's again some power of t, but what is the power of t? Is it a bigger power or a smaller power or the same power perhaps? So this question mathematicians ask for purely curious reasons. And then they also asked it because apparently there are some arguments when you study other models in the plane where you need to sum over all simple trajectories. So you want to know how many of those are. And then it turned out that actually it was asked before, and not even by physicists, by a chemist. So Paul Fleury, who won a Nobel Prize for polymer chemistry, he wrote a paper and then a book where he studied position of polymer molecules in space. So here there is an actual picture of DNA, well, normally, DNA, if you really unwind it, will be a very, very long molecule, so it won't fit in your cells. So the total length would be like 2 meters. So normally it's really like the picture on the right is a tight bow. But once in a while, for example, when it replicates, it has to unwind, so it has this sort of fractal shape for a while. And to model it, Paul Fleury proposed exactly the previous model from the previous slide, the self-avoiding polymer or self-avoiding walk, and a few non-rigorous derivations were done. So what do I mean by derivations? It means that there is a sort of logical sequence which argues that some theorem is true, but it's not a mathematical proof. So for mathematician, it's a conjecture. For physicists or chemists, it's sort of a derivation which works as long as it is supported by experimental evidence. And what Paul Fleury derived, which actually later was shown by Dejean, another Nobel Prize winner, to be a wrong method, but now we know that the answer is correct, just the method was wrong, is that on average x goes away t to the power 3/4. So self-avoiding walk goes further away than a random walk, which is quite logical because it's not allowed to return back. And then physicists came and Bernard Nienhaus, and he made a still unrigorous but more reliable derivation. And first he derived this 3/4, but also he said that c of t is mu to the power t, which is easy mathematical theorem. But on hexagonal grid, mu has to be equal to this interesting number, square root of 2 plus square root of 2. And moreover, he deduced that this formula can be made more precise. So there is exponential term, but there is a power law correction. And while the exponential term depends on the grid, we still don't know what is mu for square grid. Then this correction is t to the power 11 over 42. And it's very rare that in mathematics you see such numbers, especially in his case, 11 over 32 arose from some algebraic considerations, which seemingly were very far from these fractal curves. So we are not there yet to explain all of this. So what we were able to do some years ago with Hugo Duminil-Copin, we have shown that on hexagonal grid, indeed, mu is equal to square root of 2 plus square root of 2. So the number of trajectories of length t grows like mu to the power t with this value of mu, and this value of mu is actually twice cosine of pi over 8. I should have written it on the slide. So how do you decide what is the growth rate of c of t? So there is a standard trick in combinatorics, and you even see it sometimes in school, that to know the growth rate of c of t, you need to write this series c of t times x to the power minus t. And if mu is the growth rate, then the series will converge for x bigger than mu and diverge for x smaller than mu. So we need to find the radius of convergence of this series and to prove that it's square root of 2 plus square root of 2. It turns out that this series is not a very nice combinatorial object. So first we rewrite it as the sum of all self-avoiding walks from 0, x to the power minus lex. So these are exactly two same series. And then we work with the second one. As I said, it's not very nice to work with, so we want to multiply it by something. And what can we look for in a walk besides legs? So there is a simple combinatorial consideration. The other thing we can count is the number of turns. And the number of turns we count turns to the right with plus, turn to the right with left with minus, or actually rather the other way around. Usually left I count with minus and right with plus, being a complex analyst. So this is the formula. So you add e to the power I alpha times the number of terms. If you are not comfortable with complex numbers, you can just use the Euler formula, which we had above for arbitrary number alpha, and then you put here cosine of alpha times the number of terms with sine. So this is a function you get, you fix the origin here, and it's a function of an edge z. And it turns out, and this is the main lemma of our paper, that if you choose appropriate alpha p over 8 and appropriate x square root of 2 plus square root of 2, then this function satisfies the first rule of Kirchhoff. Now it's an interesting physics connection. So Kirchhoff rules are for an electric current on the edges. So if you have some current, you can think electrical current or water current through the edges. There are two rules. Nodal rule that the amount of water which comes into vertex is the same as the amount which comes out, so nothing is leaking. And the loop rule that there is no sort of swirl around any face, because otherwise you could put perpetual moduli. So what we prove that this function f of z satisfies the first rule of Kirchhoff if and only if x has this formula. And that actually tells us that we have some local information, but the local information, as Kirchhoff teaches us, tells us some global information. The proof is rather simple. It's really basically you study, it's kind of like changing tracks in a railroad. You take a picture where you arrive at one of the neighbors, neighbor A, and then you see how you can amend it so that you arrive at B and C. And apparently there are two pictures to deal with, where you arrive at something where you've never been, then you can prolong your train tracks. Or you arrive at something where you have been, and then you can just switch the rails. And then it's a pure combinatorial consideration. And it turns out with these numbers, you have this Kirchhoff nodal rule. And from the local rule, Kirchhoff tells us that we can deduce some global indexes on F. It's easier maybe to see with water analogy rather than with electric current, because if you have the first rule, it tells that your water pipe system is never leaking, so nothing leaks. If nothing leaks, when you take a big piece of your water system, the amount of water which comes in is the same as with what it comes out. So we can sum along a very long contour and see that the result is 0. So the proof is very short. It's one of my shortest papers. So it's like the whole proof is less than 10 pages. Can be explained to high school students. I tried it in the wild. But the interesting thing is that I heard about this when I thought that it's a combinatorics question, but it uses probabilities and uses complex analysis. And we could never have arrived without physics intuition. So I can explain combinatorics intuition to get to these numbers, but really how we arrived at this was some physics intuition with conformal field theory, paraferments, and all such. And it's, but the proof doesn't use it, but we couldn't have come up with it without it. And it actually generated more interesting question, this proof, because we still have the question about L over 32. And it turns out that to prove it, it's enough to prove the loop rule, the second rule for our function f. It doesn't hold that I have checked, but maybe it holds asymptotically. And if someone proves it asymptotically, then we will know everything about self-aware walk in the plane. We'll know this 3/4 and 11 over 32 rigorously, thanks to our work and the work of Laura Schramm-Werner, which make transition from conformal invariance to these interesting numbers. So this I find very interesting because it's a question which you could have asked just mathematically, but also if you ask it from the physics or chemistry direction, you add more intuition and more beauty to this question. And then another example, which actually I'm still working on, it was even more interesting for me because it came from biology. So it came from my Geneva friend and colleague, Michel Milenkovich. So here is pictured with a chameleon, chameleons are really cute. And he brought me this picture on the right and asked, is it similar to the picture on the left, which is one of the pictures I earned my salary with. So this is on the left is a picture where you just do a random covering. You toss a coin for every hexagon and you cover it white or yellow. And on the right, it's actually a covering of a back of an ocellated lizard who has almost ideal hexagonal back. And are those pictures similar? well, if you have been looking at percolation for long enough, you immediately say that it's not. There are more blacks here than greens, but then you also notice there are some other correlations. And then, of course, Michel, well, he wanted to trick me, and he tricked me, but then he already knew the answer, that they are different. And then he showed me this movie, which is, wait a second, is the movie playing? Yes, now it's playing. So it's a movie, it's 2.5 years of lizard. So it starts as a some sort of pattern which has nothing to do with scales, which is the case for many lizards and other squamates. But then all the scales turn green or black, and once in a while they flip around. And Michel's conjecture was that this is actually a cellular automaton. Now, I was really surprised by this conjecture, and the thing is that cellular automaton, it's a very well popular subject among mathematicians, but also it's very popular in popular literature. So they were introduced by John von Neumann, who tried to explain how from simple rules something complicated like our universe can arise. And he got to automaton with 19 states and rather complicated rules which could generate computer or universe or anything. And the most famous one is John Conway's game of life, which is much easier. It's not the easiest rule which can generate everything, but it's still quite easy. So each cell has 8 neighbors, diagonal and sidewise, and they are black, which are alive, or white, which are dead. And if a dead cell, white, has exactly 3 neighbors, it becomes alive. If a live cell, black, has too many neighbors, 4 or more, it dies. 2 or less, it also dies because of loneliness, overpopulation. And it turns out that it's complicated enough that with big enough patterns, you can model universe or modern computer Turing machine. So here there are some examples. It's stable configurations which don't change. For example, here, every black has 3 neighbors, so it stays black. And all whites, they have less than 2 neighbors. But there are periodic of different periods, 2, 2, 3, 15, or they are moving. And actually, there are even more exciting things. There are things which produce moving things. There are things which reflect moving things. There are things which eat moving things. There are things which combine two moving things with some logical operators. So you can really, well, build a computer out of those. If you can build a computer, you can model universe. Now, when he showed it to me, I immediately remember that when I was young, when I was 10, I read a popular book about cellular automaton, and there was a picture of seashell, which it was claimed that it has a cellular automaton, but one-dimensional. It had a graph that was growing line by line and showing cellular automaton, which actually is called rule 30. That's the simplest one, which has Turing machine. And he said, yes, though it's very interesting, it's very hard to biologically study seashells. Many people tried with DARPA grants or other military grants because there are very potent toxins in seashells, but they're very hard to keep in the lab. So we don't entirely know what is happening with them, besides that there are different proteins and sort of that because of that there is different color. But indeed that exists. But in our case it was different because it was two-dimensional and it was with real time, not these snapshots. And the other thing is that in our case it was clear that it was a bit random. But random cellular automaton also arise in mathematics. So for example, the Glauber dynamics for the Ising model, so it's slightly more complicated than a picture of percolation. It's model of ferromagnetism. It can be modeled with this easy automaton where you flip a cell with this probability where it depends on the number of same spin neighbors. So he was more thinking in this direction, and it's also a thing which I studied. And what he already did, he already numerically with his students got the coefficients which produce the same picture. So there was a correspondence between cellular automaton simulation and the lizard, a very good one with very good correlation. And the question was how to pass mathematically. And there are a few steps, and this was done in few steps. The first one was to get some sort of physical or chemical explanation. And fortunately, that was done by none else by Alan Turing. And what he suggested is that the patterns in animals, they arise from a heat equation, which we already sort of saw its manifestation as random walk. So heat equation describes diffusion. So if you have derivative of u in time equal to its Laplacian, then what you just get, well, you had a black spot, it will diffuse through everything. But if you add interaction between different spots, then you can get complicated patterns. So the first, this equation was written by Kolmogorov some years before, but they didn't. They wrote it only online, and they didn't see any patterns. And what Turing did, he didn't have access to computers by that time, so he did some experiments by himself, and he got interesting patterns like this one. So with different reactions, you can have all sorts of things like stripes, circles, dots. And the reason is that if you have at least two, or in our case, it's three different chromatophores, and you have a relation between them, which is activator inhibitor. So one of them, it increases the production of the second one, and the second one kills the first one. Then you get this vicious loop that the first one boosts the second one, and then the second one kills the first one. If there is no first one, then there is no second one, but then the first one again appears. And that it turned out that it sort of works very well. And though Turing suggested it in '50s, it only was proven fairly recently by Japanese for the zebrafish. So what we did was to try to understand why this can lead not to this picture on the right, where the stripes go across the scales, but rather to this discrete picture. And that is a mathematical part. So we show that if, like for this lizard, you have a thinner space between scales, so the diffusion coefficient between scales is smaller, then we can show rigorously that the Turing reaction diffusion equation, it boils down to a discrete equation on a discrete lattice. And we even have an exact formula for the coefficient. And that holds if the scales are small enough. And it was actually my sort of maybe the star moment as a mathematician, because I wrote this formula and he said, well, it's not possible. Why do you have square root of 3? You're pulling our leg. I said, well, it's because hexagonal lattice, 60 degrees, cosine and sine. And then they come next day running computer experiments overnight and say, it's a perfect fit. And moreover, it turns out that there are bigger scales on the tail. And again, our simulation exactly reproduces what you see there. And that in turn can be related to probabilistic cellular automaton. And this is work in progress. We just submitted a paper to PRL last week. And interesting enough that this automata is very much related to the antiferromagnetic Ising model in its renormalization picture. So this is sort of the multi-step thing, which involved learning some chemistry and then some mathematics and some numerical experiments which are in progress. And you see, it's a question from biology, which leads to very interesting mathematics through chemistry and physics. And I think that here I would like to thank you all for your attention. And I hope I sort of made a nice snapshot of how we mathematicians do work.